Okay, so immediate apologies to the audiovisual folks. I'm going to try and play a video that is stored in the cloud. So I don't know if people remember this, but let's see how the sound comes out. So my aspiration is not to be different. I just want to be like everyone else for the things that aren't special. So hold on one second. Let me close that. Okay, can everyone see the slideshow?
Yes.
Okay, yes. Excellent. So one could argue, of course, that the Very Large Array is radio astronomy in the cloud, and the impetus for building massive facilities, large facilities, is because no one else can afford to do them, and no one else would want to do them. So the year that Monty Python came out with The Life of Brian was, strangely enough, the year before the dedication of the Very Large Array. And it was started in 1972. Now, I don't know how many people can remember where they were in 1972, or if they were even around in 1972. But I don't believe any of the people laying the track in 72 could have believed that this instrument would still be functioning in the 2020s, and probably still has another 10 years before anything to replace it can be constructed. So to say that we have the long view is an understatement. It takes 10 years to build, and then these instruments must run for 20, 30 years with open science as their objective. So I want to be special for the stuff I build, for the hardware that observes photons from the sky. The rest I do not want to be special. So we'll focus on the VLA, although I encourage you to go and look at www.nrao.edu to see ALMA and the Very Long Baseline Array, and also the Green Bank Telescope. They are all different. But the VLA is 28 antennas, 25 meters, so 70 plus feet across. So I'm not sure how big the room is, but it's probably about 25 meters across. And they have 8 cryogenically cooled receivers. These are basically single pixel cameras, but they look at frequencies from about a foot down to less than 1/8 of an inch. So, 0.6 centimeters radiation. And that's 50 gigahertz at the high end. So 3 times a year, we actually pick up the each dish and move them out. So they go from 2/3 of a mile. This is deconfiguration, where they're all clumped together. And this gives a lot of sensitivity. A lot of photons get captured from one point out to 23 miles. And that gives a lot more resolution. And some observations actually require all 4 configurations to see tendrils and filaments, and also to see diffuse clouds. So it is a very unique instrument, but one observation could take a year or more. And then you add onto that the proposal time to actually get your science to run on this instrument. And someone doing a PhD doesn't want to wait 2 years. So how can we accelerate science? So the idea of the Very Large Array Sky Survey, or VLASS, as we call it, is to map the radio universe visible from New Mexico. So we'll do about 80% of the sky over 7 years. There'll be about 100,000 high-resolution data cubes produced. Each one of these is tens to hundreds of gigabytes in size. We'll catalog at least 100 million radio sources. And because it's 3 epochs, 3 photographs of the sky, we'll actually be able to see if something disappeared or got brighter as we stack these multiple epochs. Coverage is 2 to 4 gigahertz. And it takes about 5,500 hours, so a major chunk of the time on the VLA. So this was a large project. And the product will be about 2.2 petabytes, to give some scaling on this. And at the moment, the archive is only 4.2 petabytes. So it is a major chunk of change. So there's the full sky. This is back in 2017. You can see we're building these tiles, view of the sky. 2019, we did the first image of the full sky, first epoch. Then 2020, just finished at the end of February, the second full sky epoch. And then 2024, we will complete the full survey. So a brief summary of why my life is slightly hard. This is how an aperture synthesis radiometer works, interferometer. So basically, each of the pairs of dishes, they are single pixel cameras, talks to every other dish. And so you get these interference fringes. The further apart they are, the higher the resolution. So you can see in the top left, very high frequency interference. And you can see the phase shifts that they rotate around. They have different wavelengths. So that's great. How does that help us? Well, in Fourier space, you build up this, call it visibility. And you can see the shape of the VLA. Of course, it has each symmetric pair of baselines. And so you build a snowflake. Then you get the raw visibilities out of that. You Fourier transform it, and you get a very raw image. That then has to be processed and iterated upon to remove radio frequency interference and all other artifacts to get the actual image of what you would see if you could see the radio spectrum in the sky. And it's important to know that we see radiation. We're very specially adapted to see visible light, which is a very, very, very small snippet of the electromagnetic radiation. We can represent that as red, green, and blue colors. Each one of these pixels is actually 16,000 colors separately captured. So if you think of this as being a cube, it's got, X, Y, and then it's a very long pencil rather than a cube of information. And these lines, these fringes, give you the information around rotation and vibration molecules in space, and of course also GPS satellites. This is the noise we have to abstract out because each of the dishes is looking at a single point in the distant sky, and the GPS satellites tend to cancel out, but they are very bright. Constellation satellites, so we're in negotiations with SpaceX, let's just put it that way. So processing needs, and I've summarized this as CapEx versus OpEx, simplest thing. It comes down to, if you're paying for this, then you're not doing science unless this is doing science. And why wouldn't you just buy it and do it yourself? So each of the three sky epochs, we can afford to wait 28 months between the next scan. And so we bought 30 nodes. These are 3 gigahertz, 24 cores, half a terabyte of RAM. And these are sufficient for quick look images and continuum processing. So where you stack up and collapse all the colors. They'll keep up over the 7 years of the survey. But if you want to do the real data cubes that people want to look at, because I want to find out where carbon monoxide is in this galaxy, and I want to see how fast that's moving towards me or away from me as it red shifts or blue shifts, it would take 16 years. So we're out by an order of magnitude. But hey, 300 nodes. So we went to AWS, and we have strategically employed cloud services. For example, we had a calibration error where some of the dishes were pointing the wrong place, just a little bit offset. So we had to reprocess with that knowledge. And we did that. We did it for a month, and we dropped 50K, and we got back on track. But that 30 nodes running flat out will be 60K a month of operating expense, compared with 300K if we bought them, which we did back in 2019, and 30K a year to host it somewhere on the campus of New Mexico Tech. So they cover their costs. And that gives you an order of magnitude over the 7 years of this scan. Now, how are we going to catch up? How are we going to do these cubes? So working with Moran, HT Condor is certainly a great option for abstracting the resources out so our workflows don't change and our processing models can remain intact. And the other thing, the opportunity, is that we have minority serving institutes that we partner with, and they will get their own processing capacity. But the important thing is they will train their staff not only on doing radio frequency interferometry quality assurance and learn how to use our software code, the Common Astronomy package, but also, how to do system administration, how to do data flows, how to do workflows, how to do HT Condor. So that's a very interesting partnership. And I think there is a very tangible benefit to being able to walk up to processing and say, this is what this is doing, rather than pointing to a receipt for how much AWS you used. So to summarize, we are not special. We do not want to fly one person to the moon and beyond. That is not our business model, especially for cyber infrastructure. We basically want some school buses to reliably shuttle data for the next 7 years. But we reserve the right to surge when it snows, when we have a problem, and that's the value. And the big thing is that the workflow should abstract this out. They shouldn't mind if you're using in-house or surge and beyond, but you have to be aware that when you're facing a large, unpredictable expense, that you really have to justify that. Okay, hopefully I'm under time. Comments, questions? I think I am the last one, so back to the host.
Great. Thank you, David.